All right, Module 2, Computers and their Business Applications. This may be a review. This may be very simplistic. This may be all new for you. We're going to be talking about computers and their components. It's not going to be terribly in-depth, but you want to have a good baseline understanding. There may come a point where you're in a senior management position and we're buying all new information technology or upgrading our existing systems. You want to be able to speak intelligently about some components and systems with the experts. You don't need to be an expert yourself, but you want to be able to understand some of the lingo that goes on it. So let's define a computer. Well, it's a machine that accepts data, inputs and outputs. Whatever the machine gives us, it processes it with little or no human intervention, and then it gives us an output. And it does that with instructions. That's the programs. These are step-by-step, very clear directions for that computer to understand the task at hand. And they're written in a language the computer can understand. It's not English. It's not something that can be very read and understood by your average individual. These are languages like C++, Ruby on Rails, a whole bunch of different things. And different languages are tools that we can use, and different languages are better at doing certain tasks. As with anything, a computer really lives by garbage in, garbage out. If you give it bad data, it's going to give you bad outputs. It doesn't know any better. A computer can't think. If you transpose a number, it can be an extremely obvious mistake, but the computer doesn't know that. If you move a decimal point or something, the computer will calculate on what you give it. The computer program, if we want to write it, we need to identify exactly what needs to be done, and we need to have a method. And again, we're talking about that programming language. Some languages are better at doing tasks than other things, and some languages are becoming more obscure. Every once in a while in the news, we'll hear COBOL pop up. COBOL is a very old computer language dating back to the 70s. There's not a lot of people that are proficient in COBOL, but a lot of retirement systems for Social Security, for state retirement, was written in COBOL because these systems were developed in the 70s and they were cutting edge then, and they work until they don't. And then somebody needs to come out of the woodwork somewhere who can fix it in COBOL. But the cost of upgrading these systems to a modern language is so astronomical, or the entire database is written in a language that is incompatible with a modern language, that we're stuck using COBOL. So much so that even though COBOL was developed in the 70s and they stopped teaching it years ago, IBM is starting to develop new courses for individuals to become proficient in COBOL again. And they're setting up cloud COBOL servers that people can log into and experiment and learn inside a COBOL environment. So let's talk about some components of a computer system. Well, we have hardware and software. You've probably heard these terms before. Hardware is your keyboard, your mouse, the CPU, the hard drive. These are the physical devices in your system. The software is the operating system, Windows, Mac, Linux. They're the programs you're running. Word, Chrome browser, Microsoft Teams. These are things that you can't touch them. They're not physical devices, but they allow all that hardware to be immensely more useful than if it was just sitting there without a software. The CPU, central processing unit, sometimes you'll hear this referred to as the brains of the computer, maybe the heart of the computer. Modern CPUs really have two components. The ALU, which does all of your high math calculations, your floating point calculations, and your control unit, which tells the computer what to do. If you look at some older systems, really, mid-90s and earlier, you would have a separate math code processor that would do a lot of the higher floating point calculation. You would still have the CPU, you needed that, and the CPU could do math. It could do a lot of the arithmetic calculations it needed to run the system, but it might be a little slow. So you would have a math coprocessor to boost that up. And really that was like Windows 3.1 and previous. I think my last Windows 95 machine is a math coprocessor, but that was an option at the time, wasn't necessarily needed. Multiprocessing. A lot of computers today will have multiple cores, quad core, dual core, and it goes up and up to astronomical numbers. And really all this is your system can do a lot of multiple calculations at once. These make in complex programs easier. Video rendering is much quicker on a quad core machine than a single core machine. Same thing if you're doing a lot of programming, scientific analysis, you need that processing power. On the flip side of it, if you just need a system that an analyst can pull up some Excel spreadsheets, you don't need an extremely fast, multiple core machine. That's an extra expense. So you really want to buy the system, buy the tool that's right for the job. All throughout your laptop or desktop, you have ports on the side, USB ports, maybe FireWire. If it's a desktop, you might even still have some sort of parallel or SATA, external SATA drive. These are all buses. They're a link between your computer and exterior devices. USB is Universal Serial Bus, if you didn't understand, and that's just communication pathway for everything that's inside your computer, inside that case, inside that laptop, to talk to something outside of it. You have some sort of disk drive or storage media. It could be your hard drive. This could be a hard drive is your spinning magnetic media. This could be a solid state drive. This is where we're storing and retrieving your information you're working on. I don't like the term CPU case, but the text uses, this is just the enclosure. This is the metal plastic box you have on your desk, on the side of your desk. This is the chassis that your laptop is in. And that just, it keeps everything safe, it keeps everything secure, and it provides some protection. And it also provides a method for cooling to effectively be used, because inside your case, inside your laptop, there is a fan. You may have a water-cooled system, but it allows channels for airflow to remove heat effectively. Heat is killer for computers. The hotter it gets, the slower it'll go, and eventually it'll crash. Your motherboard is the largest component inside. It's this large PCB printed circuit board that it's home for your CPU, your BIOS, your basic input-output system that tells the computer what to do on initial startup. You plug your memory in, you plug all of your devices, your internal and external devices plug into your motherboard. That's kind of where everything sits and resides. As with anything, we want to make sure we have a good foundation of the history of it. This allows us to speak more intelligently about a topic, and it knows where we came from with computers. Computers are broken up into different generations. Your first generation dating back to the mid to late 40s. These were early systems like the ENAC. You may have learned about this in a history class, and they rely on vacuum tubes. I'm learning that more and more students don't know what a vacuum tube is. And it looked like a little light bulb. It would glow. It made of glass, and on the inside of it, you had an anode and a cathode. And this is how electricity would transfer through it. It would change values. And these were replaced by transistors in your second generation. And transistors, when transistors hit the scene, this is where electronics got immensely smaller. Before this, computers would take up a literal room, an entire room for a computer. TVs were large. Stereos, well, they weren't stereo then, but radios were large. Record players were large. And the reason for that is because all the vacuum tubes. Some of these vacuum tubes could be 3 or 4 inches in diameter, but you needed that to control the electricity flow through it for different components. You can replace, let's take a look at an old console radio from the late 40s. It would be 4 feet tall, 3 feet wide. It would have a big speaker, but it wouldn't be needed. But the vast majority of that space would be taken up by all the vacuum tubes and components in there. When transistors hit the scene in the late 50s, now all of a sudden you have a radio in your hand. Instead of an entire room of a computer, it could be fit into 2 or 3 racks. When we get into integrated circuits in the mid-60s, this is when computers get even smaller and they could fit on your desk. In the 70s, we're getting even smaller. Cray supercomputers. Look these up if you're not familiar with it. They're very, very early supercomputers. A really interesting late 70s styling to them. They almost look like furniture, but they're immensely small. A Cray computer, some of these things may be, 5 feet wide, 6 feet tall, but it was so much smaller than the supercomputers of the 50s and 60s. And the fifth generation, what we're in right now, we have multiple processing. We're getting into cloud computing. We're getting into very, very advanced processing power. And the speed and the storage capability that we have today is just astronomical, even compared to the early 90s. There's a big advantage for using computers, and this almost doesn't need to be said, but we know that computers are faster and they're more accurate than human, and they can store data better than any individual can, and they can retrieve that data faster. That's why we use computers, and that's why we rely on them so much, but we still need human oversight. Let's talk about the accuracy of it. Computers can do calculations out to an almost infinite number and give you extremely accurate information. The example here is, when you're approaching landing, whether it's a space shuttle, which we don't use anymore, or even SpaceX Dragon crew module, the computer in there is doing so much calculation on reentry to make sure that that capsule, that vehicle gets exactly where it needs to be safely. Any miscalculation, a decimal off, or a 9 that's really a 6 or whatever, can either destroy the mission or can throw you somewhere that you definitely don't need to be. The data that we store is immense. One computer will know more than you ever can. It can retrieve it in a quicker way. And when we put this on an industrial scale into our servers, into our server farms, we can just store vast, vast amounts of data. We're seeing more input devices being available to your average consumer. Obviously, you have a keyboard, a mouse, or some sort of touchpad or touch screen. But we're seeing a lot more optical character readers, magnetic readers, better cameras and images that your computer can use to input from and get more. Even 10 years ago, using QR codes was very difficult. I think it was the late 90s, a company called QCAT, C-U-E-C-A-T. They developed a little handheld barcode reader that you could plug into your computer, and it was a way to quickly get you to companies' websites, informations, interact with commercials. They tried that, and really all it was a barcode scanner. I had one. You can pick it up at Radio Shack. I think they were giving them out for free. But the idea was you would buy something, maybe a bag of chips. It may have a QCAT barcode on the bag, but you'd scan it, and boom, you would take you to that manufacturer's website at the speed of dial-up internet, and you can interact with them. And it was ahead of its time. Really, it was a QR code that we saw in the mid to late 90s. Output devices are not just your computer screen or your speakers. They could be printers, they can be plotters, they can be a 3D printer can be an output device. We're giving it an input and it is processing a physical output. What kind of memory devices do we have? Well, we have our main memory. This stores your data and information, and it's usually volatile. This is your RAM. As soon as you turn your computer off, as soon as you unplug it, everything in there is just gone. But it's extremely quick memory. And what I mean for that is, everything you're using in your computer right now, what you're seeing on your screen, the program you have, this is living in your RAM, random access memory. It's extremely quick to access and manipulate. But when you save it, your computer takes it from the RAM and stores it into your secondary non-volatile memory. This is your hard drive, whether it's a spinning media or a solid-state drive, maybe a USB, or if you burn it to a disk. This is your archival storage, because as soon as you turn it off, it's still there. Your hard drive still holds the information, whether it's powered up or not. Same thing with your USB device or your CD that you just burned. So what kind of main memory device? We talked about RAM, random access memory. Like we said before, it's volatile. As soon as the power is pulled away, it goes away. But it's extremely, extremely fast, and that's where everything you're seeing right now. But we also have cache RAM, and this stores recently accessed memory, and that lives in your processor. All of this works together for your computer to operate and to process. We also have ROMs, read-only memory. They're little chips and they're non-volatile. Same thing, you pull the power, the information is still there. Data can't be written to it. Caveat, we'll talk about that in a little bit. But typically you're not writing to this again. This is where your BIOS is stored. So the BIOS is the basic input-output system. As soon as you turn your computer on, before you enter your Windows, your Linux, or your Mac operating system, your BIOS does a quick system check. You process here, your processor is installed, this is how much RAM you have, hard drives here, check, 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 and then it starts to boot up and hands everything over to the operating system. This comes pre-flashed from the manufacturer. You can perform BIOS updates that will update and change it, but that's really as close as your typical user is going to get to writing to your ROM. Then we talk about programmable ROMs, PROMs, or EPROMs, erasable programmable read-only memory. Physically, they all look the same. You can tell an EPROM quickly. It's because it's going to be a little chip, maybe, half an inch by up to 3 or 4 inches. I've seen some of them, but there's going to be a little window on top of it, and it's typically covered by a sticker. And the way that we erase that is you put UV light on it. So sometimes you have a little UV light box. If it's exposed outside in the sun for hours and hours, it'll erase it. But this is how we can write to this information. If you think of older, like your Nintendo 64, Sega Genesis, these used ROMs, PROMs, programmable read-only memory. That's where the game was stored. It wasn't, we didn't have optical media back then. It was extremely fast. You can read this information very quickly because you weren't waiting for a CD-ROM to spin up or to access the information. And early computers, your IBMs of the late 80s, early 90s, really relied on a lot of EPROMs because at that point, end users at home could take the EPROM out, put it in a programmer, and flash different programs, different BIOSes and things to really cater their computer experience. But now we do a lot of that inside the operating system itself. You may have heard me talk about supercomputers already, but there's different classes of computers, just like there's different classes of everything else, automobiles, airplanes. If you want a really simple computing machine, that would be your sub-notebooks and your notebooks. These are like your Chromebooks that you see. They really have a limited task. They have limited processing power. They may rely solely on the cloud like your Chromebooks. These aren't devices that you're going to be doing video editing on or some really intense coding, but you can do your email. You can go on social media. You can do a lot of the basic tasks. They come at a low price, great battery life, and they're good for a lot of the users. Then we get into personal computers. These are probably a laptop, desktop that you're using right now. Really all around good workhorses. They'll do almost anything you throw at them, and they're upgradable to an extent. Your sub notebooks and notebooks, really what you get is what you get. I don't think I've ever encountered a Chromebook that you can increase the RAM in it. It's just is what you get. But your laptops, your desktops, generally they are upgradable. Then on the higher end of the spectrum, we get into our mainframes, our supercomputers. These are very large industrial business grade things, massive storage, massive processing power. The supercomputers, these are things that are working on cures for diseases, processing information from spacecraft and telescopes to model stars and their movements. Just really, really high-end industrial pieces of equipment. We're going to wrap this up. We're just generally talking about the operating system. You can have really great hardware. You can have the best machine in the world. But if the operating system can't really utilize that, you're not using all of your functions and all of the processing power. The operating system is just an interface between the computer and the user. And operating systems make this extremely easy. Your GUI, your graphical operating system. We have buttons. We're not using command lines to talk to systems anymore like you saw in MS-DOS or very early Apple computers. We have buttons that you can click and manipulate and drag things around. It makes the computer experience very, very easy. And it increases your efficiency by having these computers do incredibly complex tasks, but it has very little user input. And that's the point. If we can have an extremely powerful system, user-friendly, we can accomplish really great things. I know this video went really long. I didn't intend on doing a 20-minute video, but as you can tell, this is something I really enjoy talking about, and I can go real in depth, especially with some of the history in computer development and on a really, component level discussion for each of these things. You don't need to know all the nuts and bolts about this, but I want you to have a very general 30,000 foot view of computer systems, a little bit of their history and how they interact between your hardware and software. If you have any questions, please reach out to me. Thank you.